They set it very close, very small value, so it can be run. This is a problem of dual clamping. For genetic, we do not use the dual clamping. We first of all we random set. Okay, this one solution. The background of this one, and we use the genetic algorithm try to mutate, try to change the dot here, and from dot here we can produce more. Okay, and the black one is eliminated. The black one is eliminated. Just the good one. So and we do it in many generations, many times. At final, when the generation pass to end, the solution is close to the top. Because if this one is good, then we can include it. It will be a palette, right? And then if you get to some that's not too far from this one also. If this one is good, so it's muted, not too far. And sometimes it goes over with another one, so it can be get some thing around here or something around here, but sometimes it's not good, so it's done. Okay, so at the end, we have a set of solutions that close to the optimal, but not exactly, but close to the optimal. So this is the idea of the genetic algorithm. We can get the near optimal solution, but not real optimal in many times. But how we know? Nobody knows. Actually, nobody knows, because the problem normally, this is an example that show you to understand it, not too difficult. But in the real world, the space is not the field like this. This can be the n-dimensional space that has many number of parameters, such as more than 100 parameters. So the optimum is not like this one, but we have a lot of peak inside the space, then with high dimensional space. So you can actually you cannot know what is it. You just know the full solution, that's enough. You can see if we get this one or we get this one, this is enough. Maybe, right? Because it's close to the top. It's not the best, but it's close to the top. The genetic algorithm can guarantee this one. You can get the good solution, but it may be not the top one. But normally it's a good. Okay, let's see the example. This is a classic example that normally we use it for describe the genetic algorithm. And also they can use this problem can be solved with other algorithms. We call it traveling salesman. Have you ever heard it before? Traveling salesman. The idea is you have the city, okay, and the salesman needs to go to every city, okay, for one time, only once. And the best way to go is the summation of the distance that the salesman's travel need to be minimum. So is this a mathematical problem, right? Because we know what is the minimum. Like this one, we have 8 of cities, and we know. So when the salesman go to this kind of city, we can call it like a string, right? Okay, such as for this one, it starts with 3, 5, 7. This one is mean the salesman go to Dublin first, and then go to Beijing, go to Tokyo, go to Venice, London, and at the end it is return. This is one solution to pass of the cities. And this one is another way to do. How do you know which one is the best? We need to know the distance, right? Okay, I will. Okay, this one. Yes, the dot here is city, but this is simulated 30 city. We can calculate distance by Euclidean, right? This so we can know. But if you want to know all the possible cases of this, you need to have around 900 link 900 distance values, because each one can be close to 30 others, right? So 30 25, 30 is 900. And now we are going to use the calculator to solve this. The chromosome is, first of all, the chromosome is a list of cities. Okay. So next, we need to check how the genetic operator works with this problem. Normally, the idea of the mutation and crossover is just an idea to do, but not exactly for the programs. Normally, when we apply the program to the operator, we need to check how it works for exact versions. Okay. Such as this one. We cross over here, we just choose the parent one, and then choose the parent two. And we set the position to cross over. And then in the position of the crossover with select here, we copy to the sheet. And the rest others, we will order with the parent two. Only this gray area is for parent one. Others go to for parent two. Why? Okay, let's see. From this one we know, okay, we will cross over parent one here and parent two here and fix this one as a crossover. Okay? And after that, parent two begin with 2, right? But 2 inside here. So we skip, start with 5. We copy 5. And then 7 inside the gray, so we skip 6 inside also. The next is 8. We copy 8. Okay? And 1 inside, 3 and 4 is not inside, so we move. This is the way. Because in the program, when you use different encoding, the different way of your operator need to be changed a little bit. Okay, so you need to know how to adapt this one. This is depends on the setting of the user. So it's free for users to set. And mutation normally we set like this. For this program we choose one position and choose another position and then we swap between the first and the second one. So for now we know how to do it and how to cross over of traveling server. Okay, let's see. This is 30 seconds. If we write down the solution, can be like this. It can be skewed. Somehow we go from here and jump it to another way. That is nice. This is and if we calculate the distance for summation is 945 or something like that. For simulation. Okay, and then we use the crossover imputation. You can see that the best solution is shortened. Okay? The big thing still exists, but some others is connect each that close together. Okay? And when we iterate more, the distance reduces. Iterate more. You can see that the solution is close like a edge. Okay? Okay. And this is a overview of performance for running overall 1000 generation. You can see that this time this is a distance. This time have trying to decrease. When the generation you run it many times, the best solution, the performance of the best solution is increased, right? And At the end, we know that, okay, the solution is not changed. So this time is circulate here. So it means that this one, we can get the solution from the rest. And you can see, in each time you run, you have many of operations. So you have the best one and the worst one, right? And the blue is an average. You can see the best is go to the optimal very fast, right? But anyway, if you still run, the worst will close to the best also. And the average. If the best and the worst is close to each other, you can imagine that, it may be close to the optimum right now, so we can stop. For this one, actually this depends on you, but for me, I will cut it off around here, because the best and the worst is really close. It's green. If you generate more, it's nothing, right? Another example is like find the best one. The first one is Turing survey. And there's the equation for Turing survey. I need to check the idea first. You get it or not? Okay, not too difficult, right? That's one. We will use genetic algorithm to find the best one. Start from here. Go to. We can call it as a clip row. Okay, it's like a clip coordinate. Okay, and we begin here, and we need to know how to move here to here with. Okay, this one is a list that we need to study to set the components. Okay, let's see. First of all, we will present the part with the binary code in this program. Okay, such as we encode with if we go not, we will encode with 0 0. If we go yes, with 1 0. Sounds and yes. Okay. So finally, if we have the part from here to here, so we have the binary string, right? Okay, binary string. And the binary string here can represent the set of form. This one, if for initialize, we can generate 3 different of body part. Okay, with different 3 colors: the black one, the red one, and the blue one. This one is a little bit difficult to see because we mix these 3 parts together in the same value. You can look at the red one, we go up, go down, and finally get the blue one, go up, and finally stop here. And the black one, move in here and there. We can see that this 3 is also get a solution. Some get a solution. The black and the red, but the blue is not. The blue also. But you can from this one, you can see that. But sometimes they may not finish. It can be moved some way and end here. Can be possible, right? If we generate this random, it can be possible. And so from this problem, we can actually have some variety for this one. The first one, for this example, I fixed the range, but in real, maybe we can change the range also. Such as if you sometimes the string can be long like this, okay? Sometimes it can be longer. But you need every time if you add, you need to add 2 bits because 2 bits for one move, right? You cannot add only 1 bit or 3 bits. And the figure function is you need to sum x sum from this one. Sum the step and find the distance between here and at the end of the path. Such as the path ends around here, so you need to calculate how far from here to here. This is the fitness function. Okay. Okay, and the way of selection is to select the destination with the level threshold. Okay. From this one, you can calculate the probability, the chance that the select is proportional to fit. Such as if you generate 10, you can fix the ratio. That you want to choose just 4, something like that. Another 6, Q. Okay. Or if you choose just only the best one, this can be called it's like a greedy. So just the best one solution and you get it. Okay. And also multiplication is means if you want to generate new population, you can use crossover application also in this program. Okay, let's see from now. From this program, what is the crossover? In this one, we will use the 1 point, we call it 1 point crossover. We have parent 1, we have parent 2. Okay? And for this example, we use this part, the red part from parent, actually it should be parent 1. Should come parent 1, and the blue part from the parent 2. By fix this one. And the mutation here, we have 2 steps. First of all, we need to select which we want to mutate. Count it first and what is the position of the mutation. And after that, we just mutate from 0 to 1, 1 to 0. But anyway, from this one, mutation we need to calculate the number of mutations. And the position of them, each one, each position of mutation. Such as in this example, the mutation in 3 positions, from here, here, and the mutation here we use only 1 column. Okay, and from this one, the border we use, we set this for 1 by 4. The number of population size is mean in every time is line, the number of chromosomes that we store in the system is only 4. The genome is 60. So it's in that, for this setting, we fix range of moving. 60, this means move 8 times, right? 1, 2, 3, 4, 5, 6. To maybe we can move back like this because we have 8 times. Okay. And the fitness is step. Okay, the step that actually this means as the end of the S step and the square from goal. In that distance from between 1 to the end of the move. Okay. And propagation we use greedy, so we just choose the first one. Oh, 2 of the 2 because we have crossover. Okay, let's start. Try to initialize this one. First, we random the 4 operation. Okay, with 16 bits. We have parent 1 and parent 6. And then 4. Okay, and this is for random. So, for each one. Sometimes some population they move, go up, go down, something like this, move back and here. So finally, for population, for the first population, this time from green to here is 4. 1, 2, 3. Okay. So we can calculate this one to form of population. Which one is good? From this 4, which one is good? The first and the fourth one. Okay, this one is not good because the distance is 5 and 6. From there you can see that the solution can be, it looks strange because sometimes they move and they move out. Because it's random. So normally when you set it, for the first initialize, you don't know where it's moved. Right? So that's random, not care. It's not too much. And then, okay, so from this one, we select P1 and P4. Because P1 and P4 is separation out of 4, right? Okay. And then we use P1 and P4 to create an incorporation. The first one, the way we create is we use crossover first and then mutation before. Mutation after. Such as this one. Then make this one, this from operation 1, the black one, and operation 4 from the blue, and we make it as the solution comes over here. And we take mutate to position for finally we get it. Another way. We can set a new position. From the blue one. The blue one is the same as this one and the red one. Okay. Maybe this is just an example because normally it can be produced from P1 and P4. Normally from this one, if they set that, it select from P1 and P4, it should be P1 and P4 2 times. But different position of the crossover and different position of the relation. But this example, they choose P2 and P4 and use the same way. Okay, so finally, okay, they have this selection, okay, and they produce this one, and then they copy. They said that this one is an incorporation. 2 survive and 2 new. And then equate again. Let's see. They test new generation. Okay. The P1 and P4 is meant for the same thing because not big change, right? And P2 and P3, you can see that P2. Oh no. P4 go to P2, right? This is go to P4. The red one are down here, but the P3 here is moving up and go to go. So the distance is 0. Okay, finally we get this. We get the solution, right? Okay. So from this one, this is a second example that you can produce, you can set the problem, right? And try to use the encoding of valence string of the solution and try to use crossover application to make a new generation. And set some function to evaluate, okay, as a fitness, and then choose and select. And then you use this kind of process to evaluate and get the better solution in each time. Okay. Any problem for